Hello everyone, I'm Mateusz Malinowski. I will talk about my journey with visual question answering. I will give you my motivation, why I believe this is an interesting learning problem, even if you are only interested in vision. I will also talk about some related topics that I have been working recently. So I will start my talk with years 2014-2015. These years were very transformative for computer vision. We were quickly and successfully moving away from hand-designed approaches towards more data-driven methods. Deep learning was becoming increasingly more and more popular in various fields of computer vision or natural language processing. However, in computer vision at that time, it is used most successfully in the image classification. Here we have a single image and a single question about the content of this image. Like in this case, pixels are forming an image of leopard, and there's a question what is in the image, and this answer labeled leopard. But look around. Scenes are much more complex, quickly escaping this simple paradigm of having a single label per image. I have many questions about the scene. Where is the lamp? What is the color of the TV? What is on the table? How many sofas are there? There are, however, not only many questions, but also many different interpretations of the question that is grounded in the image. Take this question, what is behind the table, which is at the bottom left corner. If we took the observer-centric frame of reference, we would get the answer shown in the red box. If we took the object-centric frame of reference, we would get the answer shown here in the green box. Therefore, I believe it is much more realistic and perhaps interesting to ask not one question about the image, but to ask multiple questions about the content of this image. This generalizes the single image single question classification task and also requires a more holistic approach that involves object detection and some spatial reasoning. And since there is a language involved, we also expect some kind of natural language understanding. Finally, for such a holistic system, we would also need common sense capabilities. In fact, there are a few recent datasets that represent common sense reasoning in the form of visual question answering. But visual question answering is not only about language, it's also about evaluation of the visual system. But first, I will give you this simple task. The task is about seeing the real reality. It's easy to think that all visual systems should see the real reality, and you should also see the real reality. But please have a look at these three patches in the circles. They have names A, B, and C. What are the colors of A, B, and C? Which two of them have the same color? So, what is your answer? A and C share the same brown color and B is orange? Well, if we take the context, the surrounding away, you can clearly see that all these patches are physically the same. The real reality, so to speak, even though that psychophysical experience, the subjective reality, so to speak, sees something completely different. These two realities do not match. Moreover, we are also subject not only to color illusions, but also geometrical illusions. In this case, I am asking if both shapes of both tables are the same or they are different. So it turns out that these shapes only appear to be different, but they are objectively congruent, just 90-degree rotated. Okay, so what I'm trying to say here, you may wonder. We do have a seemingly faulty visual system, and yet we can use the same system to solve many different tasks. In the end, we are quite functioning agents, aren't we? But then how to evaluate visual system of our artificial agents? I think that we should likely do the same, do it on the results of their actions or on the answers. So from this perspective, visual question answering can be seen as a behavioral test of visual system. This means that we can study the problem independent of the representation. For instance, in object detection, the task is to find bounding boxes. But are bounding boxes the right representation of the visual scene at the first place? In visual question answering, you only care about bounding boxes if they improve the overall performance of the system. But there's of course much more to the visual question answering story. Visual question answering involves language and vision, and as with many other language and vision tasks such as image captioning, this one also requires grounding, either implicit or explicit form of grounding. In this slide I am showing a more explicit variant where language tokens are matched with image tokens. Moreover, intelligence requires handling various tasks and should not only be limited to classification or detection. What also excites me about visual question answering in this context is that we can encode the task in the form of a language, and then we can study the problem of task-dependent representation. Or we can basically see how the agent behaves once we give the problem, the task, or the question at the beginning. Finally, there are many different datasets for visual question answering. Each has its own properties that model some part of a more general phenomena. Some are synthetic, some are naturalistic, some deal with videos, others deal with images or physics. I'm quite a big fan of all these awesome works. I also believe that visual question answering is broader than just language and vision that are obvious to candidates. And I believe that there's also much more into visual question answering, which I argued so far. For instance, there are a few recent new directions in visual question answering that I find particularly interesting. All of them are connected to different datasets. This thinking, about the problem formulation and dataset that makes the problem more tangible, it's a very important thing. Often when we are thinking hard about the problem, we might also find that existing datasets are somewhat insufficient, not model the problem in the way that we like or we care about. And then when we create a new dataset, then those new datasets might actually lead to new directions. And there are some variants of visual question answering tasks that measures the degree of so-called visual reasoning. For instance, if you take this image here into account, you can see a question. Each question provides a new reasoning task. To answer this particular one, we need to go forth and back between the scene and the question and to think about it. So there is at least this sense of feeling that something algorithmic is needed to solve this problem. Prior datasets were more perceptual with shorter questions, where spatial aspect didn't play that big role. Here also grounding of spatial language is much more pronounced. I will pause here to give you some time to answer this question. Since most questions relates two or more things, we thought that perhaps we should encode some relational inductive bias in the network. And here it works as follows. We first build a spatial tensor. Next we concatenate the visual features from the spatial tensor with question features. And finally we use a pairwise operator that operates on n squared objects. Each object is this multimodal vector. The architecture, this one, has shown to work pretty well on the Clever dataset. And the Clever dataset is basically this synthetic dataset built for visual reasoning with an example image that you can see here. However, computations in relation networks are rather intense. The network operates on n-square inputs, and this doesn't scale up that nicely. However, if we had an oracle that could tell us which inputs are important and which are not important, we would get a much more scalable system. And this actually also leads to hard attention. So let's say that we have a scene with many different objects. And our task or a question is about some property of triangles here. Like how many red triangles are in the scene. If we could focus only on the fragment of the visual scene, we would first simplify the problem by reducing the amount of interference. In practice, we could also use more sophisticated but presumably more time-consuming processing or reasoning units. So this is roughly the idea behind the hard attention and some form of the motivation, why to use it, to cut out some fragment of the visual scene. I also believe that hard attention will become more important in the future when we start dealing with larger resolution images. And this is because this is one way of scaling down the computations. However, there is also some evidence that hard attention is biologically plausible, and I will show it now.
The monkey business illusion. Count how many times the players wearing white pass the ball. The correct answer is 16 passes. Did you spot the gorilla? For people who haven't seen or heard about a video like this before, about half miss the gorilla. If you knew about the gorilla, you probably saw it. But did you notice the curtain changing color or the player on the black team leaving the game? Let's rewind and watch it again. Here comes the gorilla, and there goes a player, and the curtain is changing from red to gold. When you're looking for a gorilla, you often miss other unexpected events. And that's the monkey business illusion. Learn more about this illusion and the original gorilla experiment at theinvisiblegorilla.com.
So we have achieved some improvement over the vanilla relation network, which is quite cool. I will not discuss our method, instead I just point to our paper, which is the last reference here. However, in general, learning hard attention is a quite difficult task, and it's still an open problem how to do it well. But it might be much more impactful than soft attention counterpart, and I gave some arguments why I believe that this will be the case. However, how far we can go with the image-based reasoning? So here's a thought experiment. Suppose that we have a relational statement. Lamp is on the table. After seeing hundreds of images, we can say something about the preposition on, but it would rather be a shallow understanding of this proposition. Something like that. We could relate position vertically. Something is on something if pixels in y-axis of the first something are larger than the second something. However, there's much more into the meaning of on. For instance, we know that if I remove the table from the lamp, then the lamp will fall down. So on has something to do with support as well, not only about position, and also about counterfactual reasoning or intuitive physics. So this has motivated me to work in a more embodied or situated setting, where we have an agent interacting with the environment. With that using, for instance, reinforcement learning. So that's where I also became interested in grounded navigation, where questions are instructions and the answers are the final destinations. But if you want to train a navigation agent using reinforcement learning, then you can start from building complex synthetic environment, or perhaps you can seek for a more realistic one. And to appreciate realistic environments, let us have a look at this picture on the right. Can you spot all the visual and language ambiguities that we need to resolve? For instance, if you follow the left arrow for the exit literally, you would bump into the wall. That is, the real world is ambiguous, and yet you can navigate in this ambiguous world. Okay, so if you have just flown to a new city and want to reach your final destination, what would you do? You would follow language directions, head southwest, turn left, turn right, and so on. So we have built an environment based on Street View with real images and topologies of the existing cities, and with instructions from Google Street Map. These are on the one hand synthetic, on the other hand they capture some aspect of the real world as they are used, for instance, by drivers for the navigation. Next, we train our agents only from these egocentric views without the access to other privileged information such as a map. They have access to instructions, thumbnails that are small images of the intermediate destinations. We train our agents on south of New York City, and then we evaluate it on north of New York City, or sometimes even in a completely new city such as Pittsburgh. Often such a drastic transfer is difficult since different cities have different visuals. For instance, buildings look different in different cities, and especially in different continents or cultures. But also topologies of those cities varies often quite a lot. So for instance, in New York City there are many intersections at the right angle. Our agents are doing reasonably in easier cases. Step by step is only about grounding instructions into percepts and actions. We always give the current instructions to the agent. In a more difficult, incremental scenario, agents need to choose instruction, but they know when to choose this instruction. So this knowledge is given to the agent. And finally, the goal is the most challenging scenario where agents need to follow instructions, choose instructions, and also decide when a new instruction comes. However, when we look a bit closer into the results, we can observe that some agents that only see images, that is, they don't see instructions, they are still performing quite well. So why is this happening? Let us have a look at what the agent is doing. Can you spot a problem? It seems that the agent can find proper destination by following the traffic. And many streets in Manhattan are the one-way streets. So this reminds a bit of the language bias problem in visual question answering, where we can get correct answer even without giving an image. But here it works other way around. We give no instruction, so no language, but we are giving images, and only images. Imagine now that you are a small child born in a bilingual family. One of your parents speaks English, another French. Sometimes you cook together with one parent, and another time you cook together with another parent. Even if you don't see the same event twice, and sentences might also be different. For instance, one day you hear I need to mix eggs with flour. And another day you hear je casse les œufs, which means I break eggs. If this situation is happening more often, you can understand that if and x are referring to the same object. So this is our setting here. We have unpaired corpora of two languages with also unpaired videos. And a scientific question: how to build a translation system between two languages. Towards this goal, we have extended the existing how-to 100 million dataset to also other languages. Most notably, to non-European languages like Korean or Japanese. Here we have some set of videos with narrations, for instance in English, and another set of videos with narrations, for instance in French. This is unpaired corpora, with the goal of pairing words between both languages. For that we have built a model that have one branch per language. Let's say that one branch is for English and another branch is for French. We first embed these words. Next we use adapt layer, that is just a linear transformation. And the role of this transformation is to adapt words between both embedding spaces. During training, we alternate between videos in different languages. To train, we use a self-supervised loss, called here multiple instance learning noisy contrastive estimation loss. Actually, there is an impressive progress on unsupervised word translation without paired corpora. These methods often rely on finding a good linear transformation between words from those two different languages. However, good results are often associated with similar languages, such as English and French. So can we improve the results on less similar languages like Japanese and French or English, for instance? We use Muse as a baseline. This is one of such successful unsupervised methods for word translation. This method relies on good initialization of linear mapping between the vocabularies of two languages, and the quality of initialization affects the performance of the method. In this work, we argue to use adapt layer from our method as this initial mapping. When we do it, we get a marginal improvement over the baseline on English to French translation. But if languages are less similar, like English and Korean, then this difference is much more pronounced. Overall, we find that vision, and in particular our method, helps the most when languages are different. Our training corpora have different statistics. Or when we don't have many textual data, but we have access to videos, to visual data. So this can potentially help in languages that are less well represented on internet. Okay, so that's it, and I hope that you have more questions.